Yeah, thank you very much. My name is Hanno Jacobs, and the work I'm going to present was done together with Philipp Mertsch and Self-confinement. I also want to thank Enrico for making like a good introduction to what I'm going to talk about. This saves a lot of time for me and really helps your understanding of what I'm going to present, which will be nonlinear propagation of low energy cosmic rays from supernova remnants. I also want to show the nice plot by Carmelo Evoli, where you have the cosmic ray spectrum. Supernova remnants are mainly accelerating protons, so the upper line, and I will focus on energies which are actually a little bit to the left of the plot here, so at very low energies. As he already explained, the particles are mainly scattering with waves at which they are resonant with, so that the lambda rates of the particles is roughly proportional to 1 over the wave number. So what I will show is that the particles can actually produce their own turbulence at exactly this resonant wave number. And because then they have more turbulence upon which they scatter, they will inhibit their own diffusion around the sources. So why is this interesting? On the left over there, you can see a picture made by the Hess collaboration of the supernova remnant W28. And also, as Enrico showed you, in clouds, there can be pion production, and then you can observe gamma rays. This is what you see there. These observations hint that the diffusion coefficient is suppressed with respect to the interstellar medium diffusion coefficient by a few orders of magnitude. Furthermore, and this is what I plotted on the right over here, where I put the flux against energy, the black points over there mark the Voyager data. So for the first time in the history of mankind, we have actually probes outside of the solar sphere of influence, and because the sun also produces some effects at lower energies, we are now able to measure like the local interstellar medium for the first time. And what I will show in this work is that this process of self-inhibited diffusion is able to explain the shape of the Voyager data a little bit better than in standard scenarios. So let me start. What is the physical setup we want to look at? It's also already like similar to the plot showed by Enrico before. It's like we have a supernova remnant that is expanding in the interstellar medium. We have a background magnetic field. These are the lines shown here. And we have cosmic rays that will be accelerated at the shock and at some point will escape from the shock acceleration region. I there assume that they simply follow power law. They will mainly propagate along one direction. So the picture of the scattering before is only like parallel to the magnetic field lines. There you have the propagation perpendicular to the magnetic field line is inhibited. So until roughly correlation length of the magnetic field, you can assume that this is going one-dimensional, and afterwards it's going to three-dimensionals, and then the particles will escape in all three directions quite fast. So what do we have to consider to describe this on a theoretical level? This is the Parker transport equation here. This is similar to what Enrico also showed before. I focus on the main part which are interesting for us, which is here the diffusion coefficient. Then we have an equation that is describing the waves at which the particles scatter. And there the most interesting part is the cosmic ray streaming instability, which will generate more turbulence, and damping terms, which will make the turbulence go away again. So the coupling terms are then the streaming instability, which is proportional to the spatial derivative of the phase space, and the diffusion coefficient is anti-proportional to the power in the waves, simply because if there's more turbulence, the particles scatter more often. So this is a setup that has been done by a lot of people before. At higher energies, so here energy loss are neglected. If you remember the plot from Enrico before, you could see that at higher energies, the energy loss time is rather large, and only at very low energies it is starting to become relevant. So what they did is they consider that the supernova converts roughly 10% of its energy into cosmic rays. Then the particles are accelerated by the shock to a power law, and then escape into the interstellar medium. What they find over here is that the cosmic rays are, with a streaming instability, confined closer to the source. So this gives the distance to the source. This is the pressure in cosmic rays, and this is the diffusion coefficient. You can clearly see that they are closer confined to the source than in the dotted lines, which mark the test particle case. The different colors then mark different times. And what you can see is that at late times, which are over here like roughly 200 kilo years, the test particle solution is recovered. And at early times, the diffusion coefficient is suppressed by up to 2 orders of magnitude. So what I will focus on here is lower energies, and it is important to consider which medium we are in of the interstellar medium. And the ones that I will focus on are the warm ionized medium and the warm neutral medium, because they are, for some reasons that I'm not going to explain now, the most interesting at low energies. The main difference between the two is that the alphane speed, so the speed at which the waves propagate and also the efficiently coupled particles propagate, is larger in the warm neutral medium due to inefficient coupling of neutrals at low energies. So we have damping process in turbulence. This is really relevant to consider. We have ion neutral damping, so it's momentum transfer of the moving ions to neutrals. We have Farmer-Goldreich damping, which is interaction of the turbulence with external background turbulence, for example, produced by the supernova remnant itself. And we have nonlinear Landau damping, which is interaction of the beat of two waves. And what you can see here is that the ion neutral damping is usually the dominant process. So what I contributed new here is that we have to consider energy losses at low energies. These are ionization, Coulomb, and pion production losses, but especially ionization and Coulomb losses at low energies. Then additionally to previous work, I also consider the cascade of turbulence. So if any one of you has ever looked into turbulence, for example, if you inject turbulence on large scales with a hose in water, they are very long, and the turbulence starts to get smaller and smaller further away from the injection. And this is what this term describes over here. So my results are, I initially start with the top hat profile, so all the particles are contained in the supernova remnant, and then they start to propagate outwards. So again, over here, this is at very early times. You can see, so 10 kilo years, you can see that these 100 MeV particles are confined closer to the source than the test particle solution marked in the dotted lines here, and the diffusion coefficient suppressed by 2 orders of magnitude. So if we look at later times, then we see that this effect of the suppression of the diffusion coefficient, and therefore the difference to the test particle solution marked here, is continuing up to like 1 million years, which is a significantly longer time than at higher energies. And therefore, this is a really relevant process if you want to consider low energy cosmic rays, for example, the propagation into clouds. So how do the spectra look like? Because the particles are confined closer to the source, the spectra will be a little softer at later times, and there will also be more flux going out of the region at later times. Then you can see that I basically, in this case, for a source distance of 60 parsec from Earth in the warm ionized medium at around 100 kilo years, I am able to explain the Voyager data with like one source already quite well. However, the existence of the source is rather unlikely. So if you really want to compare to the data of Voyager, then you have to make a statistical model. This was done by Min Fan and a few collaborators, and so this is something that you can include in their work. So over here, I quickly want to show the diffusion coefficient. So what is plotted is the diffusion coefficient again, and for 100 MeV particles, and the brighter colors mark a stronger suppression of the diffusion coefficient. Then you have here on this axis the time against the spatial coordinate from the supernova remnants. And please note that the axis scaling is different. So this is significantly longer than this here. What you can see is quite clearly that the diffusion, the region of suppressed diffusion is propagating outwards with the alphane speed. And for the warm neutral medium, where the alphane speed is larger, it will propagate out of the simulation region at some point. and therefore will be dispersed. So the fact this will also have, and this is something that I will not show, is that the grammage accumulated at these energies is also enhanced in the source region by roughly a factor of 3. So this brings me to my conclusion. It is important, so like the diffusion coefficient suppressed up to 1 million years at around 100 MeV in the warm ionized medium and roughly half the time in the warm neutral medium. So this will be a long-lasting effect, even if we cannot really see the supernova remnant itself anymore. It will still make a difference for the particle spectra coming out of there. Then we have a spectral back at around 100 MeV as required by Voyager data. However, I warn again that my model over here needs a statistical approach in order to really explain Voyager data. And I also managed to increase the grammage in the near source region by a factor of 3. So as an outlook, what we could do is we could look into the propagation into molecular clouds, because there are some puzzles if we compare the spectra that we need to explain some observations in molecular clouds with the one measured by Voyager. And we could, for example, also compare it to observations like the ionization rate measured around the supernova remnant that I showed in the beginning. Yeah, this is it. Thank you very much.
We have time for a quick question. Maybe for the Voyager data that you showed, so you modeled this with one particular source. What type of source is this? Characteristic?
This is like the standard supernova remnant, so 10 to the power 51 ergs, expanding in the warm ionized, in this case in the warm ionized medium at a distance of 60 parsecs. So it's also fine-tuned to fit the Voyager data. This is the reason why I warn against like taking this data here exactly and trying to explain Voyager data with only this one.
And this is still calculated one-dimensional, so they're like large-scale magnetic field lines connecting us to.
Yes, exactly. This is the requirement of this model. Yeah.
Okay.
Yeah.
Okay. Thank you very much.
Yeah.
Let's thank Hanno again.